अस्सलाम वालेकुम स्टूडेंट्स, क्या हाल है आपके। जी, आज हम स्टार्ट करेंगे। टॉपिक जो है वो हमारा जनरल वेक्टर स्पेसेस का, और मैं वेट कर रही हूँ सब लोग ऑनलाइन हो जाएं तो फिर हम स्टार्ट करते हैं। जनरल वेक्टर स्पेसेस आज हमारा टॉपिक है। ये इसके कंटेंट्स आपको नज़र आ रहे हैं। जी, हम जो है वो स्टडी करेंगे। सबसे पहले हम डेफिनेशन पढ़ेंगे रियल वेक्टर स्पेस की। उसके बाद हम उसकी कुछ सब स्पेसेस के बारे में डिस्कस करेंगे। फिर हम वेक्टर स्पेसेस में कॉन्सेप्ट पढ़ेंगे लीनियर इंडिपेंडेंस का। उसके बाद हम कोऑर्डिनेट्स एंड बेसिस का टॉपिक पढ़ेंगे। फिर उसकी डायमेंशंस के बारे में, चेंज ऑफ बेसिस के बारे में पढ़ेंगे, रो स्पेस, कॉलम स्पेस, नल स्पेस वगैरह पढ़ेंगे हम। उसके बाद ये रैंक और नलिटी की कुछ चीज़ें हैं, ये हम स्टडी करेंगे। अच्छा स्टूडेंट्स, अगर आपको मेरी आवाज़ बिल्कुल क्लियर आ रही है तो प्लीज़ आप कमेंट बॉक्स में मुझे कमेंट करके बता दें, और फिर हम इसको फर्दर आगे जो है वो स्टार्ट करते हैं। चैप्टर नंबर 4 है आपकी जो बुक हम पढ़े हैं हॉवर्ड एंटन की, उस बुक का ये चैप्टर नंबर 4 है जो हम आज स्टडी करेंगे, जनरल वेक्टर स्पेसेस का। जी, यानी आपको आवाज़ क्लियर है। मैं वेट कर रही हूँ सब लोग ज्वाइन कर लें तो फिर आगे फर्दर हम इसको स्टार्ट करते हैं। अच्छा, सबसे पहले मैं एक्सप्लेन कर दूं कि वेक्टर स्पेस आप किसी भी सेट पे डिफाइन करते हो, ठीक है। कोई भी आपके पास नॉन एम्प्टी सेट होगा जिस पर आप वेक्टर स्पेस जो है वो डिफाइन करोगे, और उसके लिए उस सेट पे हमें टू बाइनरी ऑपरेशंस जो है वो डिफाइन करना ज़रूरी है। एक आपके पास एडिशन है और सेकंड जो है वो स्केलर मल्टीप्लिकेशन है। और उसके अलावा ये कुछ कंडीशंस हैं यहाँ पे 10, ये आपको डेफिनेशन 1 पेज नंबर 184 पे बिल्कुल क्लियर नज़र आ रही है। ये जो डेफिनेशन है इसमें ये जो 10 प्रॉपर्टीज है, अगर आपके पास कोई भी सेट इन 10 प्रॉपर्टीज को सेटिस्फाई करे तो वो आपके पास वेक्टर स्पेस बनेगा, ठीक है। अब उसमें एक और सेट इन्वॉल्व होता है विच इज कॉल्ड फील्ड, and it is represented by the capital F. The scalars involved here, like as you can see, the small k, the small m, and so on. All these scalars belongs to that field set F. The elements of this set V is called vector space, and the elements of the elements of V are called vectors, and the elements of set F are called scalars. इसकी डेफिनेशन मैं एक्सप्लेन करती हूँ। Let V be an arbitrary non-empty set of objects on which two operations are defined. First one is addition and second one is multiplication. Multiplication by numbers called scalars. By addition it means this is closed under addition, means if you take any two arbitrary vectors u and v from this vector space V, then u and v belongs to that vector space u plus v. And on the same pattern, if you take any scalar k from the set of field and u from this set V, which is a vector, then multiplication k of u belongs to that set V. This is called scalar multiplication. The first condition is that if u and v are objects in V, objects means these are vectors basically in V, then u plus v is in V, means the set V is closed under addition. This property is called closed under addition. The second condition is u plus v is equals to v plus u. Commutative law under addition. The third one is associative law under addition. The fourth property is that we have a zero vector in that v, which is called the zero vector or the identity vector, and this is the vector identity under addition. Fifth condition is that for every element u in v, its additive inverse also belongs to that element. The sixth condition is that if k is any scalar and u is any object in v, means k belongs to that set of field and u belongs to this set v. When you multiply this scalar with this vector u, then ku is in v. ओके ये कमेंट्स आ रहे हैं कुछ के अच्छा स्टूडेंट्स ये जिनको स्क्रीन क्लियर नहीं है मैं ये आपको क्लियर कर दूं कि आपकी तरफ सिग्नल जो है वो स्लो है, उसकी वजह से आपको ये क्लियर नहीं है। आप वीडियो लेक्चर बाद में डाउनलोड भी कर सकते हैं और ये बुक आपको ऑलरेडी मैंने दी हुई है। अगर आपको यहाँ क्लियर नहीं हो रहा तो आप अपनी बुक जो है वो ओपन कर लें अपने लैपटॉप पे या मोबाइल पे, पेज नंबर 184 आपके पास इसकी सॉफ्ट कॉपी मौजूद है, ठीक है। और दूसरी बात यह है कि ये स्क्रीन क्लियर है, आपकी तरफ सिग्नल का इशू है जिसकी वजह से ये प्रॉब्लम आ रही है, तो आप जो है वो थोड़ा सा वेट कर लें, तो जब वीडियो कंटिन्यूसली चलेगी तो बेहतर हो जाएगी। और दूसरी चीज़ ये है कि आप जो है ना बाद में इसको डाउनलोड भी कर सकते हो, ठीक है। चलिए, नाउ वी मूव टुवर्ड्स द सेवंथ कंडीशन विच इज k u plus v is equal to k of u plus k of v. This is basically is similar to the scalar multiplication, as you can see. Eighth condition is also similar to the condition 7. K and m both are scalars. U is vector. When you multiply the addition of two scalars with a vector, then you get k of u plus m of u. Condition 9, k and u, where k and m are scalars, u is a vector and you can write it as k of m into u. The 10th condition is 1 u is equals to u. Here 1 is the multiplicative identity, means when you multiply any vector with the scalar 1, then you get the same vector u again. Okay. तो बेसिकली ये जो हमने डेफिनेशन पढ़ी है ये वेक्टर स्पेस की है। Now we come towards the example 2. As you can see here, V is equals to Rn. Rn means n-dimensional Euclidean space. This is basically R, which is the real number system, and n means this is n-dimensional. When you take an arbitrary vector u from this set, then you have n-dimensional components here, represented as u1, u2, un. On the same pattern, when you take any arbitrary vector v, then you get n-dimensional components v1, v2, so on, vn. And when you add these two vectors, then you get this n-dimensional vector. On the same pattern, you can also define the scalar multiplication on this vector. Basically, this Rn satisfies all the 10 conditions from the previous definition. So we can say that this is a vector space under the given field of real numbers. The question is that when we change the field, then the set remains a vector space or not? This is very important and basic question. As you can see in this example 2, we have set v is equals to r of n. If we take the scalar where you have to take this k, if you take this scalar k from the set of field and if field is equals to the real line, then Rn is a vector space and satisfies all the 10 conditions. But if I take field f is equals to c, which is the set of complex numbers, then this condition does not hold, which is the scalar multiplication closed, because when you multiply any arbitrary k which is scalar and taken from the set of complex numbers with a vector u which is n-dimensional vector, then you get a vector in the form of scalar components, in the form of complex components, because when you multiply a real number with a complex number, then you get a complex number. So this vector does not belongs to the Rn. So this condition fails if I take the field is equals to the set of complex numbers. So you can say that when we change the field, then behavior of the set is also changed from different set of fields. Maybe this is a vector space, but at some time when we change the field, this is not a vector space. अच्छा, इस बात का आपने खास तौर पे ध्यान रखना है जो मैंने अभी आपसे डिस्कस की है। फील्ड के चेंज करने से वेक्टर स्पेस का बिहेवियर भी बदलेगा। जैसे अब ये Rn है, यहाँ पे ये वेक्टर स्पेस है, अगर मैं फील्ड जो है वो रियल लाइन लेती हूँ जहाँ से मैं ये k उठा रही हूँ, अगर ये रियल नंबर होगा तो ये वेक्टर Rn में जाएगा। अगर ये k जो है ये कॉम्प्लेक्स नंबर होगा तो ये वेक्टर Rn में वापस नहीं जाएगा और ये कंडीशन होल्ड नहीं करता। ठीक है, this is example 4, the vector space of 2 cross 2 matrices. As you can see, all the entries belongs to the real number system, and these entries satisfy all the 10 conditions given in the definition, and this is the simple solution of this example. You can see we have to check all the 10 conditions for this, and at the end you can see the set of 2 cross 2 matrices is again satisfy all the conditions, and it becomes a vector space. On the same pattern, the vector space of m cross n matrices where n and n are arbitrary real numbers, then this is also a vector space. This is simple explanation of the set. Now, a set that is not a vector space. Now we come towards this example. Let V is equals to R of 2. This is the two-dimensional plane. When you take any element U belongs to this R square, then we have U1 and U2. We have two-dimensional component. And on the same pattern, when you take an arbitrary vector V from R square, then you get again a two-dimensional vector. When you add these two vectors, you get again a two-dimensional vector, and this vector belongs to the R of square. This is basically defined in the statement of the question. Sometimes when addition and scalar multiplication is not defined in the question, then you have to take the simple operations of addition and scalar multiplication. As you know, when we add two vectors, then you have to add the corresponding entries of that vectors. When you multiply a scalar k, any vector u, then you have to multiply that scalar k with both of the components. As you can see, when you multiply k with this vector u, then you have to multiply k with u1, you have to multiply k with u2. But in the statement of this question, you have to only multiply k with u1, but the second component becomes 0. This is not well defined in simple cases, but in some examples, when you have given these types of conditions, then you have to check all the 10 conditions of that vector space according to these given conditions. So here the statement ends, and as you can see, when you multiply with, when you take an arbitrary vector u and v from this R square, this is simple arbitrary vectors, and you can take an arbitrary scalar k is equals to 7. You can take k is equals to 5, k is equals to 10, and any other scalar number. When you add these two vectors, then you have to use this expression given over here, and we get this two-dimensional vector which is -1, 9. On the same pattern, when you add this scalar k with u, then you can see you have to use this condition given over here, which is the condition of scalar multiplication given in this question. Then you multiply this 7 with this vector u, and also you can see the second component becomes 0, then you get 14, 0. Now comes toward the explanation. The addition operation is the standard one from R square, which is also well-known operation, but the scalar multiplication is not. This is the same statement which I have explained earlier. Now we come towards the 10th condition from the definition. Previously you can see the 10th condition is that when you multiply 1 with that vector u, then you get that vector u again. This is called the scalar multiplication. But in this case, when you multiply 1 with u1 comma u2, then you get 0 at the second place and vector becomes u1 comma 0. This is not again the vector u, not equal to u. So due to this condition of scalar multiplication given over here, the 10th condition fails. That's why the r square given in this question with these operation is not a vector space. If this operation of scalar multiplication is again the similar of the basic scalar multiplication, then this will become a vector space. But now the condition is changed in the statement of this question, in the statement of this example. So that's why this condition does not hold and the given set is not a vector space. अगर आपको क्वेश्चंस हैं या आपको किसी एग्जांपल में कोई प्रॉब्लम है तो प्लीज़ आप कमेंट बॉक्स में वो कमेंट कर दें। और एक बात मेरी याद रखें, जितनी भी अटेंडेंस आई है इनमें से कोई भी कंसीडर नहीं होगी। एट द एंड ऑफ द लेक्चर आपकी जितनी भी अटेंडेंस है वो काउंट होगी। तो ये जितने भी रोल नंबर्स आप सेंड कर रहे हैं इसका कोई फ़ायदा नहीं है। तो आप अपनी अटेंडेंस जो है वो लेक्चर के एंड में प्लीज़ जो है वो अपनी अटेंडेंस इंश्योर करें। जी, अब हम चलते हैं नेक्स्ट। इसकी कुछ प्रॉपर्टीज ये यहाँ पे गिवन है, ये बहुत बेसिक है, हम इनको स्किप कर देते हैं, ठीक है। और यहाँ पे इसकी कुछ एग्जांपल्स हैं, ये आप देख लें। ओके, नाउ यू कैन सी दिस क्वेश्चन नंबर 1 over here. Let V be the set of all ordered pairs of real numbers and consider the following addition and scalar multiplication. This is the given addition and scalar multiplication in the question. Then you have to compute u plus v, which is the simple addition of two vectors, and you have to compute the scalar multiplication of that vector with the any scalar k. Here k is given 3. Now you have to evaluate these values. Okay. In other words, explain why V is closed under addition and scalar multiplication. Closed means when you take any two elements from set V and when you add that two elements, then answer will also belongs to that set V. On the same pattern, the scalar multiplication also belongs to that set V again. This is simple the explanation of this part B. Okay. The remaining parts are obvious, and yeah, this is part E. This is as similar the example which we have done earlier. Show that the axiom 10 fails and hence that V is not a vector space under the given operations. As you can know that the scalar multiplication is given over here like this. When you take any arbitrary vector u1, u2 and you take the scalar multiplication k with u, then you get 0, k u2. But 1, if I take the scalar multiple k is equals to 1, then the 10th condition 1 of u is not equal to u due to this operation. That's why the 10th condition fails and given set is not a vector space. Okay. There are so many questions of vector spaces, like I explained that पेपर जब आपका क्विज होगा उस केस में आपको आ सकता है that prove the set of real numbers is a vector space or not for the given field R. तो आपको R के लिए वो 10 की 10 conditions जो है वो चेक करनी है. Okay, on the same pattern, when you take the field set of complex numbers, then the scalar multiplication is not true, because जब आप किसी भी रियल नंबर को किसी ऐसे स्केलर से मल्टीप्लाई करोगे जो कॉम्प्लेक्स है, तो उसकी मल्टीप्लिकेशन आपको दोबारा रियल नंबर नहीं देगा, वो कॉम्प्लेक्स देगा. तो इसका मतलब है आपकी स्केलर मल्टीप्लिकेशन क्लोज्ड नहीं है. इस वजह से आपने ये चीज़ ध्यान से देखनी है. मैं आपको प्रैक्टिस के क्वेश्चंस भी करवा दूंगी, ठीक है, जिसमें आप ध्यान से देख सकते हो कि आपको कैसे पता चलेगा कि कोई फील्ड कैसे चेंज करें तो वो वेक्टर स्पेस है या नहीं है। ठीक है, और मैं आपको क्वेश्चन जो है वो एक पेज पे बना के वो मैं आपको व्हाट्सएप ग्रुप पे भी शेयर कर दूंगी। उसमें आपको चेक करना होगा कि कोई भी सेट डिफरेंट फील्ड्स के लिए वेक्टर स्पेस बनता है या नहीं बनता। ओके, now now this is the important part of this chapter, which is called the subspaces. First of all, I would like to explain that when you take a set sim जी, आपको मेरी आवाज़ आ रही है? आवाज़ अगर क्लियर है तो प्लीज़ आप मुझे कमेंट बॉक्स में कमेंट करके बताएं। अगर आपको आवाज़ क्लियर है तो मैं फिर यहाँ से आगे फर्दर स्टार्ट करती हूँ। आई थिंक नेट का कोई मसला है जिसकी वजह से ये हुआ है और इंटरनेट डिस्कनेक्ट हो गया था, तो ये प्रॉब्लम स्टार्ट हो गई। अगर आपको अब मेरी आवाज़ क्लियर है तो आप प्लीज़ मुझे कमेंट करें और कमेंट करके बताएं। हाँ जी, हाँ जी, अब आ रही है आवाज़? स्क्रीन नज़र आ रही है आपको? स्क्रीन शो हो रही है आपको? ओके जी, गुड। आई एम सॉरी फॉर दिस, क्योंकि आई थिंक नेट का कोई इशू है, सिग्नल प्रॉब्लम है मेरी डिवाइस का, आई डोंट नो क्या मसला है, तो जिसकी वजह से ये डिस्कनेक्ट हो गया था और मैंने इसको रिकनेक्ट किया है। चलें जी, अब हम स्टार्ट करते हैं दोबारा। सबस्पेस। Now we come towards the definition. A subset W of a vector space V is called a subspace of V if W is itself a vector space under the addition and scalar multiplication defined on V. Now, the question is that what is subspace basically? As you can see, this is V. V is a vector space and W is the subset of V. If W satisfy all the conditions of that vector space, then it becomes itself a vector space. If this W is subset of V and it satisfies all the conditions of the vector space, then it becomes subspace. Basically दो चीजें हैं इसमें, एक चीज है कि W जो है वो V का कोई भी सबसेट होगा, सेकंड कंडीशन W खुद एक वेक्टर स्पेस होगा, तब वो आपके पास इस V का सबस्पेस बनेगा। अब इसके लिए हमारे पास एक रिजल्ट है कि हम W को सबस्पेस शो करने के लिए अगर इन सिर्फ दो कंडीशंस को चेक कर लें तो हम उसको डायरेक्टली वेक्टर स्पेस बोल सकते हैं। द फर्स्ट कंडीशन इज the addition, which is closed under addition, and the second condition is the scalar multiplication. Now you can see the statement of this theorem 4.2.1. If W is the set of one or more vectors in a vector space V, basically W is the subset of V, then W is called the subspace of V if and only if the following conditions are satisfied. The first condition is that if two elements belongs to that set W, then they are closed under addition, means their addition again belongs to that set W. If K is any scalar and U is any vector in W, then their scalar multiplication K of U belongs to that set W. Now, इसका प्रूफ करने की ज़रूरत नहीं है, हम इसको जस्ट एग्जांपल्स में यूज़ करेंगे. Here you can see this is the example r square and r3. As you know, r square is the two-dimensional plane and r3 is the three-dimensional space. Now you have to check that r square is subspace of R3 or not. As you know that r square is subset of R3 and r square is closed under addition. If you take any two arbitrary elements from r square, then their addition also belongs to r square. So first condition hold. And second condition is that the scalar multiplication under the given field of real numbers, if you multiply any scalar with any vector of r square, then you get again that vector which belongs to the r square. So the two conditions of that theorem holds, and r square is not only the subset of R3 but this is also a subspace of R3. बस उन दो कंडीशंस को आपने जो है वो माइंड में रखना है सबस्पेस के लिए. Now come towards the definition 2. This is the definition of linear combination. If W is a vector in vector space V, this is the element of that vector space V, then W is said to be a linear combination of the vectors V1, V2, Vr in V if W can be expressed in the form like this: K1 V1 plus K2 V2 plus Kr Vr, where K1, K2 and Kr are all scalars. These scalars are called coefficients of linear combination. These scalars can be taken from the field, and V1, V2, Vr are the vectors in that V, and if we can write a vector W in form of this expression, then this is called the linear combination of that vector W. Basically, linear combination is just a mathematical expression of multiplication of vectors with scalars under addition. You have to take one by one the vector from the vector space V, and you have to take one by one scalar from the set of field, and you have to multiply them by addition. Then this expression is called simply the linear combination. This is definition 3. If S is equals to W1, W2, Wr is a non-empty set of vectors in a vector space, this is basically set of vectors which are taken from the vector space V, then the subspace W of V that consists of all possible linear combinations of the vector in S is called subspace of V generated by S. Basically, the question is that why we take this set S. We are going to generate a span of S which is equals to that subspace W. Span means generating set. Span, S-P-A-N, means generating set. Again, revise this definition. If S is a non-empty set of vectors, this is a set and vectors are taken from this V, and W is an arbitrary subspace of V that consists of all possible linear combinations of vectors in S, means W contains all the linear combinations of these vectors, means the element of W is in the form of K1 W1 plus K2 W2 plus so on Kr Wr. This type of elements belongs to that subspace W. Then this is called the subspace of V generated by S. All the linear combinations of these vectors belongs to that set W, and W subspace is called generated by this set S and can be written as like this mathematical expression. In example 11, as you can see over here, we take Rn. Okay, now we have n-dimensional Euclidean space, and you can see the E1 is the first vector, E2 is the second, and so on. En is the last vector. The vectors span Rn since every vector v. Now you can see every vector v can be written as a linear combination of these vectors. So this is called span of that vector space. If we take three-dimensional vector space I, j, k, as you know about, this is x-axis unit vector, y-axis unit vector, and z-axis unit vector. Then every vector v can be written as linear combinations of these three vectors. So these three vectors span the vector v. On the same pattern, we can take the spanning set of different vectors. Now, the example number 14, this is very important example and based on the linear combination of the vectors. Consider you have two vectors u and v belongs to R3. These are three-dimensional vectors given as 1, 2, -1, 6, 4, 2, and show that w is equals to 9 to 7 is a linear combination of u and v, and that w prime, which is 4, -1, and 8, is not a linear combination of u and v. We have to prove that this w can be written as a linear combination of u and v, and w prime cannot be written as a linear combination of u and v. Now we take the linear combination in the form of this. As you know that we can write the linear combination as k1u plus k2v, where k1 and k2 are any scalars and w, u and v are the vectors given over here. Now we put the values of w, u and v in this mathematical expression from the question. Now we get 9 to 7 is equals to k1 1 2 -1 plus k2 6 4 2. Then by multiplying these scalars and adding these vectors, you can get this vector. As you know, this is also a three-dimensional vector. When two vectors are equal to each other, then their corresponding components are also equal to each other. Now k1 plus 6k2 is equals to 9, 2k1 plus 4k2 is equals to 2, minus k1 plus 2k2 is equal to 7. By solving these equations simultaneously, you can get the values of these scalars k1 and k2. You can solve the system of equations by Gauss elimination method, by Gauss-Jordan method, or any other arbitrary method. So k1 is equals to -3 and k2 is equals to 2. Now we put these values of scalars k1 and k2 in the previous expression of linear combination w is equals to k1u plus k2v. Now you get the vector w is equals to -3u plus 2v. Similarly, we've done all the process for the vector w prime. As you can see, you can write the linear combination as w prime is equals to k1u plus k2v, and by multiplying and adding these vectors, you get these vectors. By taking equal of corresponding components of these two vectors, you get these three equations. But the question is that this system of equations is inconsistent. So no such scalars k1 and k2 exist, because you cannot solve this system of equation, and if you solve then you get no solution. So you cannot take w prime as a linear combination of these two vectors. You can solve this system by using Gauss elimination method, which we have done earlier in previous lectures. These are simple questions based on vector spaces and spanning set. Now comes toward this exercise. Okay. Now the question 1 is that you have to prove that the given set are subspaces of this vector space or not. All vectors of the form of this. A set containing all vectors of the form this is subspace of R3 or not. You have to prove this. Now all the vectors containing the set containing all the vectors in this type, which is a comma 1 comma 1, is a subspace of R3 or not, and the set containing all the vectors in the form a comma b comma 0 is a subspace of vector R3 or not. So you have to prove this by using that two conditions, by proving that two conditions. Question number 7. Which of the following are linear combination of u and v? This question 7 is similar to the previous example. Now you put this vector a is equal to w. W is equals to 2 comma 2 comma 2. Then you make a linear combination. W is equals to k1u plus k2v. Then you make them equations by solving simultaneously that equations. If you get the values of k1 and k2, then you can say that you can write the vectors as a linear combination of u and v. If you cannot get the values of scalars k1 and k2, then you say you cannot write the vector as a linear combination of these vectors. Question number 8 is similar, but here we have three vectors, so you have to find three scalars. The linear combination, if you take this vector a is equals to w, means w is equals to -9, -7, -15, then you can say that w is equals to k1u plus k2v plus k3w, means this is the fourth vector. You can take it as like z. The vector z is equal to k1u plus k2v plus k3w, and by solving that simultaneously all the equations, if you get the values of that three scalars k1, k2 and k3, that means you can write the vector as a linear combination of these three vectors, otherwise not. Okay, now uh, come towards the question number 9. Which of the following are linear combination of a, b and c? This is similar in question number 7. Here we take the three-dimensional vectors, and here you take the 2 cross 2 order 2 cross 2 matrices. This is the similar question as we have done earlier. Now you can solve all the questions from the internet as well. So ये आज का लेक्चर भी आपका कंप्लीट हो गया है. इसमें से आप क्वेश्चंस जो मैंने बता दिए हैं वो आप कर लें. अब आप अपने रोल नंबर जो है वो सेंड कर सकते हैं. और दूसरी चीज़ मैं आपको बता दूं, नेक्स्ट लेक्चर में जो है नियरली इंडिपेंडेंस का और उसकी कुछ फर्दर चीज़ें पढ़ेंगे. अगर आपको इस पूरे लेक्चर में से कोई चीज़ समझ नहीं आई है, कुछ पूछना है, तो प्लीज़ आप वो मुझसे डिस्कस कर लें. जी प्लीज़ अपने रोल नंबर कमेंट सेक्शन में जो है वो कमेंट कर दें. अभी सिर्फ 6 लोग नज़र आ रहे हैं मुझे, तो प्लीज़ आप सिर्फ इन 6 लोगों की प्रेजेंट मार्क करेंगे. जो यहाँ पे ऑनलाइन है वो प्लीज़ अपना रोल नंबर जो है वो यहाँ पे कमेंट बॉक्स में कमेंट करें. आपका लेक्चर एंड हो गया है. अगर कोई क्वेश्चन पूछना है तो आप प्लीज़ पूछ सकते हैं. स्टूडेंट्स, मैं वेट कर रही हूँ आपके क्वेश्चंस का.